Hello, my name is Mohammed Fattah. I am a senior studying computer science engineering, um, fully graduating next week, and this is my presentation of my honors capstone for winter 2020. So my project was a project under the guidance of Critic Hayer and Dr. Alberto Figueroa of the Computational Vascular Mechanics Lab in the Biomedical Engineering Department. And my project is estimating, its title is Estimating Angiography. Um, so the problem statement, so given, let me move this. Given that we have an angiogram, as you can see, an X-ray of a heart vessel, we want to detect the fatty deposits through that. Now, for example, in this vessel, as you see, fatty deposits are places where, as we put a dye through a vessel where the dye would pretty much simulate blood flow, we're looking to estimate the pressure as the dye goes through the vessels of the hearts. Unfortunately, I would love to show you a video, but unfortunately, I cannot due to many agreements we have to sign. So I'm settling in to show you this video, imagining as you go through each vessel in the artery, you will want to estimate the flow through each one, flow through each place, and the places where there is a faster flow, then we know there might be an occurrence of a fatty deposit, because as you can imagine, like if you have very big opening, it probably flows through very smoothly. But when you have something like this where it enters from something pretty big, but then it tightens up, the pressure goes up and the velocity increases. And for example, in this artery, as we can see, in this place, actually, this is where the coronary plaque buildup is, or the fat deposition. And as you can see, we can really barely even see it in this vessel angiograph. And this is a bit more information on how it would look like. For example, in a healthy coronary artery, we have fairly, obviously, very little fat deposition, and if not, and in here we would have some sort of buildup. And this is also similar, where we have a side view image of how this buildup actually tightens the vessel. Now, why are we looking to do this research? It's because if a vessel actually gets completely blocked, the person will sadly end up having a heart attack, and then they would need a bypass surgery, which is extremely invasive and extremely dangerous. So the reason for this research is to actually even predict whether somebody might have fatty buildup. The surgery is very invasive as well. So we're looking to give doctors just more data on whether a patient might need an invasive surgery. So the first steps in this research for me, I need to find a way to segment the branches and then also through that estimate the blood flow through each branch. However, I couldn't do any of this until I actually get a binary representation of the vessel in the image. Although there is a lot of research on this, no research is perfect to get it completely done. And so I worked on exploring, doing my own research to actually just first use the multiple computer vision as well as techniques to get a binary representation, as you can see here on the right. So the vessel extraction methods that I've used are Harris corner detection, which as you can see, so what is hair corner dissection? In hair corner detection, what we do is by shifting an image by some specified amount U and V, we look to compare how much does that shift compared to the original image. And why is that important? Because we know that something happened if we've changed it. I've also tried quite a few vessel filtering operations, such as Frangi vesselness, Sato-tubeness, and Hessian vesselness filters. And the Harris corner detection, as you can see here, where we are detecting corners, as these green dots, as you can see, are actually the corners in the artery image. One thing that I saw that was very positive in this was we did not have much noise. However, we also did not cover every place in the artery through this algorithm. So although this method did actually give us some positive results, we saw that we needed more. So I moved on to working on vessel filtering operations. There were multiple vessel filtering operations in much of the research, which will be in my paper. And some of these are the Sato-tubeness, Frangi vesselness, and Hessian vesselness. Although you can barely see anything here, even with actually me improving the contrast severely, we saw a lot of problems, especially with the Hessian vesselness. We could not remove the noise. Frangi vesselness, we need to remove more of the noise, but also even improving contrast did not help. One thing that we did see some positive results from is the Sato-tubeness, and as you can see, we see some sort of representation of the just artery by itself. But even when we improve contrast, and as you can see as we will show in the next slide, we did have a lot of noise. So when we try, so one thing that we saw that we needed is actually we needed to do pre-processing to the vessel before actually applying the filters. And the way to pre-process, we did some sharpening, blurring methods, as well as adaptive equalization, where we actually modularize the intensity on the image, or the angiograph in this case. And as you can see, so if we contrast stretch, we improve the intensity. As you can, we can see more of the actual vessel and less, and probably keep the same contrast on the original image. And we can see also a representation of how the modulation has been done on through the histogram. We use histogram equalization, where we kind of improved some of the less adapted spots, and that did improve it a little, but we saw extremely amazing results from the adaptive equalization, which actually fairly less intensified some of the light areas and also intensified the vessels. However, problem is that this the adaptive equalization, or CLAHE, CLAHE, was pretty noisy, and I'll show you why. So when we applied the vessel filtering operations with this method by applying pre-processing to the image and CLAHE, we couldn't really get anything that was not noisy. We still got the same poor results from Hessian and Frangi, but in Sato-tubeness, even though we can see that there was some sort of it was able to do some sort of good work, but it was very noisy. So there was really no use. So after that, and working with PhD student Kritika, and Also, the filtering was an extremely computing intensive task. So even though we would use it, we would have to wait a couple seconds every single time to actually detect what is wrong. What are the results? So through all of that, actually, we had other research in the lab, which I cannot really discuss, as it will be hopefully published soon. But I will say that we have the research which allowed me to actually get the binary image that I was looking for. And I was working at the same time as them to make sure to see if they do not finish their research, then I can actually get my some sort of product on. But thankfully, they finished their research, and I was able to use their product. So for me, I actually moved on to the core of my project to actually look to segment the vessels after getting the binary images. And so the steps that I used to do that is, first of all, I use skeletonization. Skeletonization is a method where when we have the binary image, we will use the midpoint in the darker regions to find many midpoints through the vessel to actually connect them and get a skeleton of the vessel. And the second step is also, after actually getting the skeletonization, we'll use the B-spline transformation, which is a model fitting function, which gives us like a piecewise continuous function containing multiple polynomials, because we will have multiple vessels. This is a bit different than the linear regression models, which is only fitting one function and it's only one polynomial. And so in skeletonization, so for example, in this example here on the left of the binary image of this is actually some of the previous case of the initial phase of the distribution of blood in the vessel. And as you can see here, we are, actually these images are a bit out of order. I apologize for that, but the image to the left and to the right is a skeleton of actually a bit of a later flow of the blood. But as you can see, the skeleton is the dark black here, and it really just goes through the vessel as a skeleton. And so how were we going to use that? Our goal is now to use this data, which we have just gotten, to fit a model, a continuous piecewise model through this through this skeleton. Why is that? Because we want to estimate the distance which has been traveled through each branch. If we are able to estimate the distance, then we can obviously estimate the velocity. So in the initial phase, when I was working on finding the multiple libraries which do B-spline, which had actually very little documentation, it was a bit tough for me to use as I was using for the first time. I realized after putting in maybe like 40 hours, my thinking was all wrong. The B-spline, even though I thought the algorithm would take care of the task of actually realizing which branches to segment, it turned out that I actually need to segment the branches on my own and then fit it through the B-spline. So initially, this was the result we got. Those points here are points on the skeleton, which are in blue, which we used from the skeleton. And the point and the connected line is actually the approximation, which you see is absolutely terrible. And so I move on to actually just to test the B-spline by manually segmenting the vessels by myself. And through this, as you can see, we actually have fit a continuous model through each branch, and through each of that, we can actually find the distance that is overlapped by the model. And why is that? Because each of these is a polynomial, obviously. And since it's a polynomial, it's differentiable, and we can actually get the distance throughout these multiple branches. Now, since this was manually segmented, I need to automate this feature, which is something I should continue. This is a project that I will be continuing to work on this summer, hopefully, or actually likely. And so the first step for me, actually in the summer, will be the automating the vessel segmentation. So we'll use a method, computer science method, very well known algorithm, breadth first search on the skeleton data to find the intersection points in the vessels and then segments the vessels through that. So and also the second step after we are done with that, we'll look to estimate the velocity by using all of the data that we have from the Angiography.com video, and we'll estimate the velocity of the length of each branch at each frame. And so this is my future work will be to hopefully segment the vessels like this, and then through that we will look to estimate the velocity. Okay, so as I've told you, I will be working, continue to work on this project throughout the summer, and hopefully looking to finish it up hopefully in the fall or pass it off to another student in the fall. And a few questions that I look to answer actually right now is how did I get involved in this project? So I got involved in this project through my sister, who's working in this lab as well, and I was able, actually, unfortunately, due to so many hurdles, I actually started this project in probably about very late in January, and through all of what has gone on, I realized that I did a lot of work just mainly by myself, not being in the lab. And that was definitely one of the main hurdles, having a bit less of the communication opportunity that we had by going to the lab and talking with face-to-face with the PhD student or the professor. A few challenges that I did find, and I can probably just scroll back, due to it taking so long in the beginning to actually filter and trying to just do so many different approaches. These are only few of the things that I have probably tried and couldn't get the result we wanted just through the filtering was very frustrating in the beginning. But it was definitely a lesson to me actually to learn on how to be able to filter complex images or files. And it was, even though it was frustrating at the time, I definitely learned a lot from it. Another question I would like to answer is, how did I connect with the lab advisor and PhD student? And honestly, just the most important thing in being in a lab or really at work is to be honest. If you don't know how to do something or struggling to find a way how to do things, really just be honest. Because if you don't know how to do it, you'll never get it done. But if you ask questions, you might get pushed in the right direction where you'll be able to do and get positive results. Asking questions is absolutely the most important thing. And also, there are no such things as stupid questions. This was a quote from one of my X376 professors, and I definitely have heard that throughout many classes, because it's always sometimes something very big that we do not understand, but sometimes it's so small and we think it's so big. So definitely asking questions, and you definitely also gain your professor and PhD student respect by asking questions, because they see that you are thinking about this project. They see that you're putting in the effort to figure out ways to ask questions. That's the most important thing. And so, yeah, these are questions I'm looking to answer for you. I guess one last thing maybe I can cover is challenges. I mean, we all know, I probably actually already covered that, yeah. Anyways, yeah, so I want to give a few acknowledgements at the end. So I want to sincerely actually thank Kitty Ayer, PhD students working with, and Dr. Alberto Figueroa, because they continually guided me throughout this project, and actually very much looking forward to continuing working on this project in the summer. I also want to thank my sister Aya Fatah for introducing me to the lab, and because of her, I actually was probably able to be part of such a great research group. And it's very, very nice to be a part of a nice research group. And yeah, thank you so much for watching. I really appreciate you bearing with me through these 15 minutes or so. Thank you so much.